So let's look at this circuit. Same start point. I want to come up with a model for the current, the flow of current the instant I turn up that step voltage. It's going to end up with a steady state, is it not? Is this circuit, when I turn on this step voltage of 8 volts, going to reach a steady state current? And what will the value of that current be? Eventually we're going to reach 2 amps for the current. Will I reach 2 amps instantly? At the instant I turn it on, will the current be 2 amps? No, because initially the inductor is going to have an effect on the circuit, isn't it? It's going to build to that because there'll be an inductance, back EMF effective, that's going to oppose that. So it'll take time for the current to build from 0 to 2 amps. And the question is, what happens? How does it change? Is it a straight line? We might make a guess what that is. Sorry? No, this is what we're doing here now, is trying to predict how the current will change over time after I turn on that 8 volt supply. What will the shape of the curve look like? And also, what time will this be? How long will it be until it reaches the steady state current of 2 amps? That's what our model is hopefully going to show. So what we do is exactly what we did before. We write down what the Laplace transform is for the voltage, the inductor and the resistor. So the initial step is exactly the same as it was before. The voltage is 8 volts, which is, so therefore Vs equals 8 over S. If we look at our table, we'll find that for the inductor, which is 2 henries, then the inductance in S space is just 2S. And for the resistance, which this time is 4 ohms, then the resistance in S space is just 4. So those are our values taken from the table. Put them into Ohm's law. I equals V over R. V is 8 over S. And underneath we've got 4 plus 2S. Now, the problem is now, and this is the problem that always comes up with these, so the good news is that once you've got the idea for each type of circuit we're going to look at, you just follow the method. Again, I don't like that S being underneath here at the top. I want to get rid of that. So if I times top and bottom by S, I would get rid of that S on the top. Yes, then I get an S squared, good point Luke, on the bottom, which is, I don't want that, okay? So what I do is this. I say IS equals 8 over S times 4 plus 2S. What do we do now? If we look at our table of transforms, it will help us. If I go back to here, this one we looked at before, and we look at this one and this one, so that's this one here and this one here. If you look at this one, there's something involving an S, and this one we've got an S and then a constant term. And if we look at what we have here, we have an S and a term involving S and a constant. And so what we do is we separate these two out using partial fractions. So now we use partial fractions. Which we were doing this morning. We take our 8 over S brackets 4 plus 2S and we separate it out and say it's equivalent to some number over s plus some other number over 4 plus 2s. Because if you look at the table of transforms, we've got something over s and something over s plus a constant. So if I can find out what a and b are, we can then find the transforms. And that's exactly what the method of partial fractions allows us to do. And so we just remember that technique. What do we do first? Right, cross multiply and make one equal to the other. So we focus on the right hand side and we say a times 4 plus 2s over s times 4 plus 2s plus b times s over s times 4 plus 2s. Cross multiply, make the denominators the same. Because the denominator is the same, we can just add the numerators. A 4 plus 2s plus bs, don't need the bracket anymore, over one lot of s times 4 plus 2s. Equate numerators. So if we look at the left hand side up here, 8 equals a 4 plus 2s plus bs. And now we can find a and b by letting s equal certain values. What can I let s equal so that b disappears? Right, let s equal 0. You're on the ball today. I've just run out of board, so I'm going to just put this onto another side. Carry on. So 8 equals a 4 plus 2 times 0 is just 4, so 4a or a4. So a equals 2. Looking back, what do I do now to try and make a disappear? Y minus 2. Yeah, minus 2, because minus 2 times 2 is minus 4 plus 4 is 0, right, yeah. So if I let s equal to minus 2, a disappears. Or, if it's not going to be a nice easy number, remember what we did this morning, which is really what I was after, this bracket's got to be 0, hasn't it? And it's not always obvious. So think to yourself, this bracket's got to be 0, so I've got a little equation to solve. In other words, 2s plus 4 equals 0, and in that case s would be minus 2, but not always that obvious. So s equal to minus 2, I can say 8 equals a has disappeared, b times minus 2. So dividing both sides by minus 2, b equals minus 4. So is equals putting the numbers A and B back in to this original expression here, A over S plus B over 4 plus 2S. So we've got A over S, and A is 2, plus B, which is minus 4, so we can say that's minus 4 over 4 plus 2S. So quick recap. Got our circuit. Got our circuit here with an inductor in it this time. Step voltage. Transform them into S space, each of our components, including the voltage. Plug them into Ohm's law, I equals V over R. We can get rid of the S on the top, okay, but we're left with this term underneath. And this is the classic example. Again, you need to recognize it. That's the key, really. I've got S times by another term in brackets. So what should spring into your mind? At this case, I've got to separate this out using partial fractions. So the S term and the 4 plus 2S term. So I use my method of partial fractions, and I end up calculating the values of A and B, and then plug them back in, and I get to here. So that's my transform now. So if we look at our table and look at these two, the 2 over S looks like this one, look. A over S, where A is 2. And this bit looks a little bit like this one, but again we've got S on its own in this, so we need to get S on its own here. So what do we do? Right, divide top and bottom by 2. So IS equals 2 over S minus, dividing top and bottom by 2, 2 over 2 plus S. And we can now write down our transforms time-wise. So this IT equals, so if we look at the 2 over S term from the table, that's just A, whatever A is, which is 2. Minus E, sorry, again we've got to think of this 2 as being brought out in front of it, 2 times e to the minus 2t. Because again, this 2 at the top here can go in front and just be called 2 times 1 over relative, effectively. Yeah. Yeah. Yeah.
Oh, yeah, sorry, CPF in the table forgot e to 80.
Finally, we can tidy this up a little bit. That is correct, but we would commonly take a 2 outside the bracket to leave us with what we hopefully might recognize as an exponential growth to a limit. If we plot it in an autograph, we get something like this, which we sort of predicted. We look back at our original guess for this circuit. Look, we guessed it was going to reach a current of 2 amps. Well, it has reached a current of 2 amps here, 2 amps. But now, more than that, we can actually say how long it takes for it to get to that steady state, about just coming up to 3 seconds. So if I had a circuit with those components in it, I would have to wait 3 seconds. There would be a transient period of 3 seconds before the circuit settled down to a steady state.
Is that such